All right. Alrighty. For Cal 1, so we're going to look at actually, so in this lecture, I'm going to do two sections. They're both actually going to be pretty quick, but we're going to look at, I think it's 3.6 is implicit differentiation, and then 4.5 is limits and infinity. And you'll see, hopefully you'll kind of connect with the implicit differentiation, even though that sounds like a horribly weird word. It's actually really easy. It follows really quickly from stuff that you guys already did for finding derivatives. And the limits at infinity, you'll see when we get to that, I'm honestly just going to show you a couple of problems because you've done this before. They just didn't call it limits at infinity, but I mean, you'll see when you get to it, it's like, I actually already know it. Um, so, hold on. So let's look at implicit differentiation though. And what you're going to see here is, so one, this is not some new path. So one thing I want to emphasize, especially on the tail of the last lectures you guys saw before that test, this is not a new differentiation. This is not a new method, not a new pattern, nothing like that. All we're going to look at simply is we're going to look at what are called, and you guys should have already seen this in a college algebra class before, but what are called implicit functions. And I'll talk about the difference between that and normal functions like that we deal with that are called explicit functions. We'll look at implicit functions, and then we're just going to basically the case that we can still take the derivative of them, right? So let me actually get a problem for you guys to work. Let's say we had something, this was exercise 5. That matters for you. But let's say we have something like this. So this is a function you guys have, or this is, sorry, this is this is a relation you guys have seen before. What is this the graph of? Back to algebra / pre-cal. That's the graph of a circle. Now notice that, so one of the things you probably saw about this before, your teacher maybe mentioned, or you could even see now, is that this is not written the way that a function is normally written. How's a function normally written? So a function is normally written y equals blah, 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 and there's an x somewhere in there. There's maybe quite a few x's, whatever. But there's an x somewhere in there. So the way functions are normally written say that y is dependent on x is the independent variable, y is the dependent variable, but that y is essentially sort of created by x. Right? And in an algebra class, if they give you a function like this, they might say, hey, try to get y by itself. What problem do you run into if something like x squared plus y squared equals 9? Well, that's not the best way to ask it, but let's see what you guys think. What problem do you run into? So the problem with this is that technically can't get y by itself because we end up with something that's not a function. So again, normally functions are written this way. We call it, and the way that the word they use for that here is explicit. So this is an explicitly defined function. It's y in terms of x. The problem with something, oh my goodness, I need a better eraser. Oh, that's gonna be an issue. Let's see if this works better for right now. A little better, sure. So the problem with something like this is if you do try to solve this for y, you end up with y equals what? Plus or minus the square root of 9 minus x squared. And again, going back to an algebra class, they might, if you did something like this, you might have talked about, well, this is not a function, right? Because now we have called, one particular x value has two different possible y values that go with it. If you think about the graph of x squared plus y squared equals 9, this is a circle, radius 3. You can see it a lot quicker and a lot cleaner from the graph, actually. This is definitely not a function. For every x value, there's two different y values that are associated with it. So basically, a function in this class that you cannot, basically that you can't get y by itself, or you can't cleanly find x, y in terms of x, is an implicit function. So basically, if you can't get y by itself and get sort of get a function, the classic thing you're looking for, y in terms of x. Every x has one y value. Then we call that an implicit function. Or well, it's not really a function. So they call it a function in this class because we still want to sort of, or we're going to see we can still do something with it, but we know from algebra that it's not actually a function. So this thing is not a function. A relation, really. So this thing is not a function. But what we're gonna do is we're gonna say, so basically what we're gonna do in this section, or what we're gonna do today is, I still wanna find the derivative of y. So if you think about, yeah, let me give a little more motivation for what we're doing today. So again, I guess what I'm saying is this is not a function. And when we did all that work on derivatives, we were dealing with purely, explicit defined y, with functions, explicitly defined functions. But if you think about it, that that definition for a derivative, the difference quotient that we talked about, it works whether the thing is a function or not, right? So like that definition for a derivative was just about finding the slope of a tangent line on a curve. It doesn't matter if the curve is this curve, so I shouldn't have erased that, or if it's a nice x squared curve, x squared is a function. There was nothing about that that basically required the curve to be a function. The difference quotient still works. The derivative is still going to tell you the slope of the tangent line, whether it's not a function like this, or whether it is a function for something like x squared, right? And so again, what mathematicians kind of realize is maybe this is not a function, but it doesn't mean I can't take a derivative. I can still take a derivative. So that's what we want to look at sort of that's what we're looking at in 3.6. This is again 3.6 is if I can still take a derivative, then how do I go about doing that? And like I said, what you'll see is I'm actually not going to introduce any new technique. And we're also not going to go back to the definition of a derivative. We can actually take the derivative of this based off of what we already know. Based off how we've taken derivatives. So they're on a problem like this, they're going to say something like this. They're going to say find dy dx, find the derivative of y. So they'll say something like that, which another way to read that is they want you to find y prime. I think, let's see, for these problems, I guess it probably depends on for these problems, but I'm probably going to use y prime. I think it's, to me, just a much cleaner notation. So need to find y prime. I need to find the derivative of y. So when I look at this function, or this is, again, it's not a function, but when I look at this relation, I am still treating x, so x squared is kind of a function, but here I'm gonna start treating y as a function. So I think the one, maybe not odd thing about this, I think you guys are used to this after going through those sections on derivatives, but again, in going through those sections on derivatives, one of the things we start doing is we really treat y not as a variable, not as some number that we don't know, but we treat it as a function. It's an object that represents a whole function, right? When I say I want to find y prime, what I'm saying is this thing is a function. A y squared is not a number squared, it's a function squared. And I want to find the derivative of that function. So, huge lead up, big grand reveal. How do we go about doing this? So the nice thing about this is what we're going to do essentially is now we're going to treat the derivative as an operation we can do on an equation. So I'm gonna just take the derivative of the left and the right. Take the derivative of x squared plus y squared. I'm gonna take the derivative of 9. You don't have to necessarily put the parentheses here around the 9, but I'm doing that just to be consistent. But that's what I'm doing is I'm thinking about this as I'm taking the derivative. So even the 9, even though it's a constant, I am treating it as a function. So again, in terms of what we did with those first, 3-1 through 3-4 on derivatives, one of the things we learned is that you take the derivative of a constant, you get 0, right? But again, what we're doing in that is we're now thinking of 9 not as a number. And we're still thinking of it as a number, but we're not thinking of it not as a number, but we're thinking of it as an actual function. And the derivative of that object, function that's a constant, is 0. So that's really the trick, honestly, to implicit differentiation is we're going to start by taking the derivative of both sides. Let's see what comes out of that. And then see, again, our end goal is to find y prime. So let's start on the left here. I want to take the derivative of this. So this is now two functions being added together. And this one is x squared. And what's the derivative of x squared? So hopefully in a second. Actually, so give me a second. Also think about it. We should know. But yeah, so since I'm gonna go towards the y prime notation, so then the derivative is 2x. Easy enough. Now here's the fun part. I want to take the derivative of y squared. Again, y is a function. What would you guys say? What do you get there? I'll give you a second. I won't pause, but I'll give you a second. Think it through and tell me what you think. All right, so what do you guys think? And if you're saying 2y, so not only, so some good instincts here. So it is kind of the y squared, so the derivative should be use the power rule, 2y. The difference between the x and the y here, so the x squared itself is a whole, is a whole thing as a function. When I'm thinking about a function or even the derivative of a function, I'm expecting it to be a function, and in functions, x's are my independent variable, y is my dependent variable. Y depends on x. So when I take the derivative of x squared, it's 2x. That whole thing is a function, but this y squared, it is a power function, but again, y is a function, so y is a function being plugged into a power function structure. So what I'm saying is y squared is sort of like when we saw problems like the following, like let's say I had sine of x, maybe I should use sine of x squared, or we would write it sine squared x, but we'd have something like this, right? So this is one function plugged into another. This is sine function plugged into an overall squared function. Or let's say I had something like natural log of x squared. That is one function plugged into a squared function, right? So what I want to emphasize here, I think again, usually the only odd thing about this at first is that you got to see y now as a function, because again, when we see a y, that's the way we normally not only express it, but that's our expectation. Y is a function defined by x, right? So y is in terms of x. When I see y, this itself is a function as if it was like a sine x or a natural log of x. So the good question is, let's go back to one of your sections you just went through, just and not just a section, but kind of what you just learned with derivatives. So if I had something like this, how would I take the derivative of each of these? I actually want to give you guys a second to do that. So I want you to take the derivative of each of these. So we'll do the derivative of each of these. So I will actually pause. So pause on your side, pause on my side. Take a derivative of those. And let's pop through what you're getting. All right, so like doing the derivative of sine x squared, how would you go about doing that? Or how did you go about doing that? Good. So remember, when you have one function plugged into another, we have to use the chain rule. So like the derivative of this would be, let me give myself a little room here. The derivative of this would be 2 sine of x. So again, you're using the power function pattern overall. So 2 drops in front, sine of x. But then you have to multiply by the derivative of sine x. And what's the derivative of sine x? Cosine x. So the derivative of that would be 2 sine x cosine x. Similar play here. So when you took the derivative of this, you used the power function pattern overall. It would be 2 natural log of x, but then you had to multiply it by the derivative of natural log of x. What's the derivative of natural log of x? That's 1 over x. We might, doesn't matter how you write this, but you might rewrite it as 2 natural log of x over x. Well, the key thing here is recognizing, again, when you have one function in a larger, in an overall, you have one function plugged into a larger function, an overall pattern, that you have to use chain rule. So then again, the slightly odd thing here, I'm going to stop calling it slightly odd. So hopefully it connects for you now and then it's not odd. Is that when I'm doing the derivative of y squared, I do 2 times y, just like we did over here. But then I have to multiply by the derivative of y. So this is chain rule as well. So that's basically what I'm trying to say here is take the derivative of 2y squared, you are doing, or y squared, you are doing chain rule. Because that is one function plugged into a larger function. Or in this case, a larger structure, the power function pattern. So it is going to be 2y. Then just like our derivatives over here, we have to multiply by the derivative of what's being squared. And what is the derivative of y? So the interesting thing is over here, we knew what y was. So we could actually say the derivative of sine x was cosine x, derivative of natural log of x was 1 over x. Like it's like we actually got some action and some work there, right? But here we don't know what y is. Even though I don't know what y is, I can still say its derivative. I may not be able to like tell you in detail what it is. I may not be able to say it's sine of x or 1 over x or whatever. But I still can say y prime. I still can multiply by the derivative of y. So y prime now is a symbol we're going to use for the derivative of a function, even when we don't know the function. Because abstractly, that itself, that symbol still tells me the derivative. It still signifies the derivative. It's still something we can write on paper that's a stand-in for whatever the derivative actually is. And work you just did in the last all those sections before the test, you knew what the function was, and so it was explicit. You could take the derivative, so you knew what the function was, and you can actually say the derivative. You don't know what y is, because if we did know what y is, by the way, we could solve this for y. So that's actually why Don't know what y is. We don't know what y is. But I can still say the derivative. Derivative is y prime. Then what's the derivative of 9 of a constant? That's a 0. Now I want you to, again, hopefully have like an Oprah aha moment. Could we solve this for y prime? So again, my end goal is to figure out what y prime is. Again, I think one of the cool things you're going to see with this, or at least what's cool to me, what excites me is, again, to begin with, I couldn't solve for y. This is not a function. But I just go ahead and blithely, I just say, oh, let me take the derivative of both sides. Now, could I solve for y prime? Notice that you could. So this just algebraically, hopefully, like you look at that and you're like, oh, hell, I could actually get y prime by itself. And that's basically every time you do one of these problems, that's the response I want. You don't have to say hell if you don't want to, but oh, hell, I could actually get y prime by itself. That is the point of these problems. It's, even though we couldn't get y by itself or have y as a nice clear function, I can still take the derivative of both sides, and in a lot of cases, all the cases you're going to see in this section, right? But in a lot of cases, you can actually get y prime by itself. Then you've solved for the derivative. You didn't have to go through some of this. You didn't have to go through finding the derivative of certain functions and thinking about patterns. That take the derivative of both sides. There's a little chain rule there. So you use one of your patterns of derivatives. Use a little, in this case, power pattern, because x squared worked that way. Then you just use algebra from there and you get y prime by itself. Works pretty beautifully. That is implicit differentiation. So we'll do some more examples, we'll do some problems, but actually you'll see we don't even have to do much more for this section. That is implicit differentiation. If you do that every time, take the derivative of both sides of your original equation, your relation, and get y prime by itself. Golden. Got it. It's just algebra from there. So let's see if you guys can do the algebra from there. So, and I say that because I think you guys easily can do the algebra from there. So pause on your side, I'll pause on my side. Go ahead and get y prime by itself there. So for y prime. All right, let's see what you guys got. Oh, easy enough. Pretty much you want to move what we want to move the 2x over here. We're going to divide 2y off of it. So hopefully you guys see that pretty easily, and that gets y prime by itself. So you're going to end up with what, negative 2x over 2y. And we can cross out the 2's there. So we end up with negative x over y. So we start out with this relation. Goal is to find y prime. We found y prime. Y prime is negative x over whatever the original function y was. So notice that, so again, all this implicit differentiation, you have an implicit function to begin with, or you have an implicitly defined y. Notice that your derivative ends up as implicit. So again, explicit means y equals blah, 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 x. So it's y in terms of x. Implicit just means it's defined in terms of x and y, basically. So implicit to begin with, implicit on output. And I'm not saying it's impossible actually. So this is not to say it's impossible for your y prime to be explicit. So you might end up with an explicit function to end up with. You might end up with y prime just equals something something x, right? So not impossible, unlikely though. So this is a perfectly good result. So that's part of why I'm bringing up sort of that whole thread is implicit in, likely implicit out. So don't expect it to end up looking like some nice function. It wasn't a nice function to begin with. Won't necessarily be a nice function at the end. The goal was to figure out y prime, and y prime is there. So we've got it. That's y prime. And just as another small thread, another interesting thing about y prime here is the fact that You think about the idea of like recursive algorithms or recursive functions. So again, we're starting with this implicitly defined thing. We want y prime. So, and going back to another point I made again, the derivative is just telling you the slope of the tangent line. So in some ways, what this is saying is when we get to the end, we're saying y prime actually depends on the original function. It depends on the original y. That the slope of the tangent line now doesn't just depend on x, it now depends on the original function itself. It's kind of an interesting concept. It's kind of, like I said, it's like having a recursively defined sequence where, so if you remember recursive sequences, that means that the third term in the sequence depends on the second term. It depends on the second term or maybe the first term, but it depends on previous terms of the sequence. So in some sense, we're saying the first derivative here depends on the original function. And this maybe then the second derivative depends on that original function or depends on the first derivative. So it's the second thing is defined in terms of the first and the third thing in terms of the second. So this is that kind of pattern doesn't just happen with these sort of vented sequences that you saw in some algebra class. It happens actually very naturally taking derivatives, at least with implicit functions. So, good. As far as technique though, like that's it, honestly. So like I said, that I promise you that's actually it. You take the derivative of both sides and you get y prime by itself. So let me give you guys actually just maybe a couple other problems to play with, and that's actually going to be it. That does this section. So then, like I said, I'm going to tag on the limits at infinity. So we'll do one more section in this lecture just because you'll see it's also really quick. But let me get a couple more problems. Um, So I think let's start with something like number 12 from that same, erase this part, but it just give us a little more room. This is square root of xy equals x squared y plus 1. And same thing, they're going to want you to find, so all of these are find y prime or dx or dy dx. So now notice again, equation. So you got an equation involving now both x and y, in this case on both sides. And notice that you don't just have a number on this side. You also have function y along with other function of x here. So on the left side, we have square root of x times the function y, and on the right side, we have x squared times the function y plus 1. So the function y is just all mixed up in this. But the play is the same. We're going to take the derivative of both sides, and then we're going to try to get y prime or dy dx by itself. So that's the first thing then is we got to take the derivative of both sides. So we need to take the derivative square root of xy. We need to take the derivative of x squared y. And again, we know when we're adding pieces together, when we're taking derivatives, we can do those separately. So if these were multiplied, we couldn't. Like here, you can't do the derivative of x squared and derivative of y. You have to do that. So hopefully you kind of anticipate using a bit of, what call it, uh, anticipate using a bit of your product pattern here. But it's plus derivative of 1. It's going to be 0, which is really nice. But we need to work the derivative of both sides here. So I give you this problem just because these derivatives are going to force you to use more of those derivative patterns that you just learned. So honestly, that's in some ways I would say there's conceptually the point of this section is to teach you sort of just remind you about implicitly defined functions or relations at least, and then to see that derivatives can be implicit as well, and to teach you the technique of going through this. But honestly, I'd say the other half of why they have this section in a book or why I would teach this thing is honestly just to get you to practice using those patterns of derivatives. That's actually, it's like that's really half the point of this section. So in the last problem, we ended up needing a little bit of chain rule. This problem, probably going to need chain rule again, but also notice that there's going to be, call it a, yes, there's going to be definitely going to be a bit of product rule here. So let's sort of start working our way through here. Actually want to see which direction. Where do I want to start here? All right. Well, I don't think it'll matter really where to start. Let's start on the left here. So, and as we go through this, I do think again one of the things you'll run into in this section that I think is sort of the main thing you'll have to work on is recognizing the derivative patterns you'll need. So, for instance, looking at this left, I see a square root of x y. Notice again that this is, so overall this is an xy, this is a function x times a function y plugged into a square root. So for first, there's going to be some chain rule here because you have one function plugged into another. But then the function that's plugged in, so last time on the last problem, y was plugged into a squared function. So we just used chain rule and wrote y prime. But here we have x times y plugged in. Again, notice basically the signal for you, the thing you really want to notice is that it's two functions multiplied, the multiplication. The thing you want to notice is the multiplication. Because that means then so we'll do the overall pattern, which is going to be power rule. Remember, square root is a 1/2 power. So we'll do the overall pattern. But then we got to multiply the derivative of what's inside the square root. And to do that, you're going to have to do the product rule because that is an x times a y. That is two functions multiplied. So that's going to be the kicker. You'll see not just here, but really you see, hopefully you see it automatically here that we've got product rule here, even in our chain. We've mixed product rule into our chain rule. So, like I said, I think the bigger thing you'll run into in this section when you're doing these is more making sure you recognize what derivative patterns coming across. Then just working those out, because once you work those out, the rest is algebra. The algebra honestly may be a little long and a little annoying, but the rest honestly is algebra. So, this is, write this is xy, the 1/2 power. We're going to take the derivative of that. So the overall pattern is a power function. So we're going to multiply by 1/2. Then that's going to be xy to what power? So 1/2 minus 1 is a negative 1/2. We could talk about kind of ways to rewrite that. But then this is chain rule because I have one function inside of another. So I got to multiply by the derivative of xy. And to multiply by the derivative of xy, I'm going to have to do product rule. Basically, we need to figure out the derivative of xy. It's times y. So what is my product pattern? It's my product rule. How do I find the derivative of one function times another? It's first function times the derivative of the second plus second function times the derivative of the first. So I'm going to have to multiply. So I'm going to have to multiply by the first function, which is x, times the derivative of the second. And how do we write the derivative of y? That's y prime. And I don't need to know what y is anymore. Derivative symbolically is still y prime. And then, so first times derivative of second plus second, which is the y, times the derivative of the first. And what's the derivative of x? The derivative of x is 1. Y times 1 is just y. So this is all times x, y prime plus y. This is all times x, y prime plus y. That is now the left side of your equation. Again, I said is like I was saying. So visually, this maybe looks annoying. It maybe looks complicated. This is a bit like we've talked about, I think, in some point during several lectures before this. Don't let them fake you out with stuff that looks complicated. I promise you, the algebra plays out fine. You just got to kind of trudge your way through the algebra more than anything. But that means you got this. So don't let the visual fake you out. Then we're going to take the derivative of the right side. So we already said the derivative of 1, you already know is 0. So we're really just taking the derivative of this. Now notice that this is not a function plugged into another. This is just one function times another. So this is not this squared or square root or plugged into some larger piece. This is just x squared times y. So then what pattern are we going to use to figure out the derivative of this? That's also going to be product pattern. So this doesn't require chain rule like we did on the left, but we're not plugged into something larger. It is one function times another, so we still need the product rule. We still need the derivative. We need to do first times the derivative of second plus second times the derivative of the first. And I'm going to give you guys a second to do that, actually. So this won't be long, but pause on your side. I'll pause on my side. Go ahead and figure out the derivative of x squared y. All right, so derivative of x squared y. So I'm going to do first times derivative of second. So we should have got x squared times y prime. And second times the derivative of the first. And what's the derivative of x squared? That's going to be 2x. So from here, like I said, I'll kind of rearrange that. But like I said, the rest of this is we've got to solve for y prime. So the rest of this is algebra. So we want to think about possibly rewriting this left side because leaving it as something to a -1/2 power isn't going to help me algebraically kind of work with this. Although it may, so let me think about that. But so on first blush, so that's the rest of your job then is to kind of work this out algebraically. Notice that we have ultimately, so we got to deal with this part that's the xy, that's the 1/2. But at least minus that, ultimately we have pieces with y prime, pieces that don't involve y prime. So that's actually really promising. Again, our goal, if you're solving for y prime, then once you hit here and you know the rest is algebra, you know your goal is to get y prime by itself, which means we want to get all pieces with y prime on one side, and then all pieces without y prime on another side, and then hopefully we can sort of divide off at that point. So just generally, that's going to be, I wouldn't, again, I mean, that's mathematics, but I would call that strategy more than anything. This is gaming. So I want to get y primes on one side, the other stuff on the other side, so that I can get y prime by itself. So the first thing I'm going to do here, and this is more instinct. This is more, I look at this and I say, well, I can rewrite this. That's 2 square roots of xy. That's fine enough. Then I'm just going to try to take my instincts from algebra, start solving for y prime here. First off, we usually don't leave something in the bottom of a fraction like this because it makes it impossible to kind of separate things out and do kind of linear equation solving that we're used to. Just we get all of our pieces with desired thing you're solving for on one side, and then we start dividing things off. So um, anyway, so what that means is I'm basically going to multiply by 2 square roots of xy on both sides, because that will conveniently get rid of that denominator. And that's nice. Again, looks horrible, but that's actually nice. So we have x y prime plus y. And again, I want to get everything with y primes on one side, so I want to distribute this through, even if even if when I distribute it through, it doesn't actually multiply to anything. I want to distribute it through so that I can start isolating the pieces that with y primes on one side. So this right side is going to be uh, I will do some simplification here. So what I see is that on this first term, so square root of xy is remember with exponents in general, so with square roots, I could think of this as the square root of x times the square root of y. Square root of x is x to the 1/2 power, so I can multiply that with this. I'll end up with 2x to the 5/2 y to the 1/2 on that first piece y prime. And then square root of xy, again, you could think about it, each of them is to the 1/2 power and you're multiplying by x to the first and y to the first, so you're adding those powers. Or you can think of this xy as basically a square root squared. Either way, what you end up with is we end up with, or this is actually going to be basically xy to the 3/2 power. Now, again, what I see is I see some pieces with y primes and I see some pieces without. So let's go ahead and move things over. So basically this is going over here. This is going over here. So I end up with xy prime minus 2x to the 5/2, y to the 1/2, y prime on the left. I end up with 4xy to the 3/2 minus y on the right. Now I can factor out a y prime from both sides, or from the left side. X minus 2x to the 5/2, y to the 1/2. Then I can divide this piece off. And I end up with y prime by itself. So again, that's my goal. And once I get here, I really don't care how ugly this side looks. So spoiler alert, the right side is often going to look ugly. It's just not going to look like functions were, well, functions, but even relations we're used to seeing, right? Um, and that's okay. Again, the real world models for things are often more complex than a lot of these nice functions and relations we've studied so far in mathematics. Um, which is why it's hard to predict things. Um, so one of the reasons. Um, could leave it as it is. I think me, so this is again, I'm a human. This is where aesthetics come in. I'm going to write the top here. I'm going to write x to the 3/2, y to the 3/2, only because on the bottom we have these sort of each separately to powers. Um, actually, you know what? I guess I could write it different way now that I think about it. It doesn't matter. Actually, it doesn't. It just really doesn't matter how we write this. 5/2 y to the 1/2. That's fine enough. And that is my derivative. That's y prime. So again, trust the procedure. It gets you there. Take the derivative of both sides and then get y prime by itself. So in some sense, this is really, I won't say an algebraic trick, but it is just using a technique of algebra to sort of get you out of a situation that you couldn't have gotten out of otherwise. Because again, we're starting with implicit relations, implicit functions, which means I can't cleanly take the derivative, right? Or like I can't say y equals this thing and then just take the derivative of the right side, right? So we're in a situation we can't deal with cleanly just using using the derivative directly. So again, explicit is kind of like direct, implicit is indirect. So we can't deal with it directly. So we take the derivative of both sides, then algebra just, allows us to get y prime by itself. And so we indirectly get to the answer anyways. All right, let me make sure you guys see all that. Yes, you can. Okay. Um, so actually, let me look. Actually, honestly, though, I mean, that's kind of this whole section. I think if, well, let's just see if there's any other problems with any other patterns of derivatives. You guys didn't. Um, let's maybe look at one more problem. So we'll do one more problem as kind of my way of, in some ways, it's almost like a sign off, like a kind of, you've seen these two problems and sort of the stuff involved. Let's see if you can run one through, basically. So let's go back. Let's look at one more problem, and I think that's actually good for this section. It's 16 e to the xy. Plus x squared minus y squared. Squared minus y squared equals 10. Plus y squared equals 10. Again, hopefully you see, looking at this, at least me looking at this, I'm saying There's a bit of a mix of the first problem, right? We just have a 10 on the right side. But notice that over here, we have a little bit of chain rule here. So hopefully you kind of see that already. Hopefully you see in the e to the xy, when you take the derivative of that, what patterns are you going to be using there? So there's definitely chain rule. There's, one piece, one function plugged into another, but that one function, kind of like the last one, it's two functions multiplies. You're going to be using a little bit of product rule there too. So very common to kind of have product rule and chain rule, honestly, in a lot of these problems. And I would say, honestly, in realistic models that you'll be doing in physics, chemistry, engineering, etc. So this is not just good exercise, it's really actually kind of very much on point for stuff you're going to see in the future in real life. So good. So let's see if you can take this. So same goal. I want you to find y prime. See if you can take this all the way through. Go ahead and pause on your side. I'll pause on my side. All right, let's see how you guys did on this. So like I was mentioning, let's attack the worst thing first. So we need to take the derivative of e to the xy. And that is one, it's going to be chain rule. So the result there is going to be e to the xy, but then I got to multiply it by the derivative of xy. And that itself need product rule, product pattern. So that's going to be times, I'll just put parentheses there, I guess. First times derivative of second, so xy prime plus second y times derivative of first. It's just 1. But then that handles both the chain rule and then the product rule that you need for the derivative of xy. Then what did you guys get for the derivative of x squared? Good, that's gonna be 2x. What about the derivative of negative y squared? Again, kind of like that first problem, this is negative 2y, but then y is a function being plugged into a larger function, a larger structure. So you're gonna multiply by y prime. All that equals 0. All right, and then notice again, we kind of end up in a similar scenario where we got some pieces are gonna have a y prime, some pieces don't. Get the y primes on one side, the others on the other side, and then do your algebra from there. So actually, I'm gonna distribute through here. So this is gonna be xy prime e to the xy, and plus y e to the xy plus 2x minus 2y y prime plus 0. I'm going to move these pieces without the y prime to the right. That'll be what? This piece and this piece. Let's keep these others on the left. So we'll have xy prime e to the xy minus 2y y prime equals, going to both be negative. So negative y e to the xy minus 2x. Then we can factor out a y prime. X e to the xy minus 2y. Interesting. Very interesting. And divide off. You guys kind of get the idea from there. What we end up with overall, let's put that up here. Y prime equals 7. Yeah, I'll keep the negatives where they are. Minus 2x. So negative y e to the xy minus 2x on the top, and x e to the xy minus 2y on the bottom. That's our answer. I was kind of heard me murmur that something's interesting about this. What's interesting about this is top and the bottom are actually the same. In some sense, they're really the same form and structure. Almost, not quite. Uh, but notice basically sort of your x's and y's are switched in some sense. So they both, the first term of both of them is e to the xy, but this one is a negative y, so it's a y outside, got an x outside here. And then the back end is a -2, but here on top you have an x outside, and on the bottom you have a y outside. So literally it's switching the roles of those, of the x's and y's kind of in the top and the bottom some way. So they're in some way, it's almost like being a complex conjugate or something like that. Like they're in some ways sort of a symmetric mirror of each other, like left hand, right hand. Chirality, if you know that from chemistry. So, but yeah, that would be our answer. And again, that's everything in this section. Um, so so yeah, good. So that's 3.6 implicit differentiation. Um, like I said, let's look at 4.5 really quick. I really was gonna do a separate video on this, but it was gonna be like a 15-minute video, so it sort of makes no sense. So let's go and look at 4.5 really quick. Do I have any of the spray? Actually, give me a second, guys. I think I have some of this in my bag. Let me wipe this down a little better. Oh, sweet. So 4.5 and 4.5, they call this section limits at infinity. And kind of again, to prove my point, so way back at the beginning of the lecture, I was saying that you've actually already done this, they just didn't call it this. So to prove my points, again, let me find a problem for you guys. And we'll talk about what you've already done in a previous class. So it's not even this class. You guys have actually just done this in a previous class. Just trying to remember why they bring this up separately in a calculus class. All right. Um, let's so we can. Look at something, so I'm gonna sort of bring up 13. 13 has three parts to it. So the first part, so what they say limits at infinity. So what they literally mean here is we're gonna take the limits, all the problems in this section, you take the limit as x approaches infinity. Or a negative infinity, could be either going all the way right or all the way left. On this first one, they want the limit as x approaches infinity of x squared plus 2 over x cubed minus 1. So what I'd like you guys to do though is I'll kind of want you to think about, so they want to know as x approaches infinity, so as you keep going out right on your x values, what's the limit of this thing? So I actually want to give you guys a second to go ahead and pause on your side. I'll pause on my side. Think about this. So what I'm saying is this is not even calculus. guys already know this answer. Already know how, or at least, yeah, you already know this answer. You already know how to figure this out, or this is. So take a second and see if you can figure it out. Mm. All right, so hopefully what this brought back for you is this is just a rational function. So on a rational function, if you think about the graph of a rational function, as you go far left or far right, as you go to positive infinity or negative infinity, what kind of happens at the ends of the graph there? Good, you have a horizontal asymptote. A horizontal asymptote by definition, or at least what we know it is it's some value, it's a y value that the graph gets closer and closer to, but never actually reaches, right? That's a limit. It's actually just a limit, right? So you don't need to do anything new for this. You just need to figure out the horizontal asymptotes. So in this case, what is the horizontal asymptote going to be? Good. So the power up here is smaller than the power down there. So the horizontal asymptote would be y equals 0. That's where the y value goes here. The limit as x approaches 0. Sorry, it approaches infinity. Y value as x approaches infinity is going to be 0. So this is just horizontal asymptotes, nothing more. I literally don't have to teach you anything new. That's all this is. So really quick, to sort of remind you of a couple things you've seen with horizontal asymptotes. Um, what if I had x squared plus 2 over x squared minus 1? I wanted the limit as x approaches, matter infinity, negative infinity, doesn't matter. When the powers match, what's my horizontal asymptote going to be? So it ends up being the coefficients divided by each other. 1 divided by 1 is 1. This is 1. What about it then if we have something like x squared plus 2 over x minus 1, where the power on top is bigger than the power on bottom? So hopefully you remember that that gives you a slant asymptote, or it could actually be something other than a slanted straight line. But either way, that gives you not a horizontal asymptote, but essentially on your graph, it's going to look like the graph is going to keep going up, approaching slanted dotted line. Nonetheless, it's going to keep going up or keep going down the left and on the right. So you can kind of see for this one, even if you don't have a graph in front of you. So again, first the power on top is greater than the bottom. So this is gonna, our limit is basically, you can say there isn't a limit, or you can say the limit goes to infinity. And basically with these, you just gotta decipher whether it's infinity or negative infinity. And if you keep plugging in large positive numbers to this is gonna be a positive divided by a positive. So that's positive infinity. Again, as long as the power on top is bigger than the power on the bottom, you got a slant asymptote or something like that, means you're going to infinity, negative infinity. And honestly, that's kind of it. Let me look to see if there's just any uh, interesting problems here that I want to link that to. Yes, so a couple problems problems I wanna look at other than that. But like I said, kind of related to. So the surprising thing here is that essentially this idea of the horizontal, how we got the horizontal asymptotes with rational functions, is actually, so we'll see, even if we see some functions that aren't rational functions, or aren't classically irrational functions, the idea still actually plays out. So for instance, um, that's what the problem. Um, so on 18, they want the limit x approaches infinity, something like got 5 over x minus x over 3. And what this is not one rational function, it's two rational functions. And we know from the work we did on limits that we basically can find the limit of each of these individually and then just sort of combine them, and that gives us the overall limit, right? So that's actually your approach here. But since these are each rational functions, the way you're going to find the limit for each of these is just, again, thinking about horizontal asymptotes slash don't have a horizontal asymptote, so slant asymptote. So for instance, this 5 over x, as x goes to infinity, what's the limit on this going to be? So on this one, definitely the power on bottom is greater than the power on top, and so that automatically goes to 0. Or just another way you can think of it practically is that if you keep plugging in larger and larger numbers to this, the 5 is not changing. So 5 divided by 100, and then 1,000, and then 1,000,000, that number, the result there is going to keep getting closer and closer to 0 because you're just dividing by larger and larger numbers. So this goes to 0 one way. But this x over 3, what's the limit as x approaches infinity there? Good, that's going to be infinite. So again, you can think about the power on top is bigger than the power on the bottom. So that's slant asymptote. Or again, you can just think about the calculation itself. I'm doing larger and larger numbers divided by 3. So I'm going to keep getting larger and larger results. So this goes to, actually, does it say, sorry, it actually says negative infinity on this one. So let's maybe accurate here. That still, obviously, that still goes to 0. This one is going to go to negative infinity because it's going to be a larger negative number divided by 3. So what's 0 minus negative infinity? Good, that's going to be positive infinity. So again, another way to think about this, if you think about this overall, what's happening is this number is getting smaller and smaller. This number is getting larger and larger in the negative direction, but you're subtracting it, so it's really positive. So you're getting really large positive number plus a minuscule number close to 0. So you're still just getting a really large positive number. Or again, you could just 0 minus negative infinity is infinity, so the limit is infinite there. Good. So all of your knowledge with limits and then with rational functions works beautifully there. What about, so let's look at something like 25. Want the limit, x approaches negative infinity. Something like x over the square root of x squared minus x. Now again, notice this isn't a classical rational function. This bottom part is really a radical function, so it's not a polynomial, which makes this not technically a rational function. But it is still a fraction where you're going to be putting in larger and larger negative numbers on top, larger and larger negative numbers on bottom. So what I'm saying is basically these 3 cases for rational functions really kind of work for fractions in general. They're actually just, the reason you got these results for rational functions is because that's actually how fractions play out. So if you have some function, the bottom of your fraction, which has a larger average or overall power than the top, your limit as x goes to infinity always goes to 0. It actually doesn't have to be a rational function. It just has to be a fraction. As long as it's a fraction, it's going to play out that way. You have larger and larger numbers in the bottom compared to what you're getting in the top. So if your function on average is popping out much larger numbers in the bottom than the top of the fraction, then when you do your calculation for a fraction, it goes to zero. It just does. It does the thing. Yeah, for limit. Later on in the class, or actually later on in Calc 2, you'll talk about it. It's absolutely true for limits. Um, you'll see something called convergence and divergence in calculus 2, which takes that idea kind of a step further. But anyways, yeah, so it's true just because that's how fraction calculation works. You're popping out much larger bottom numbers on the bottom than on the top, it goes to zero. If your numbers on top tend to match the numbers on the bottom, they're within kind of a good range of each other, then the coefficients tell you the limit. But if you popping out on average much larger numbers on top than the bottom, then you're getting some calculation that's just skyrocketing. It's going higher and higher, either positive or negative, but it's just getting larger and larger, right? So again, these things you were taught before were about rational functions, but they're not really about rational functions. These patterns are about fractions. And so what I'm saying is anywhere, any function where I end up with a fraction that actually kind of plays out the same. So again, this is not a traditional rational function, but you want to think, we can still think of largest power on top, largest power on bottom. And what is the largest power on top? Largest power is 1. What would you say is the largest power on the bottom? Again, not traditional polynomial, but notice we basically have a square root of x squared. We know that algebraically we can't just break these up, but the leading term and underneath the square root is going to be the x squared. That's going to dominate my calculation there. What is the square root of a squared? It's just x. It's just x to the first power. Basically, this bottom is an x to the first power. My powers match, which means how am I going to find that limit? How am I going to find that horizontal asymptote? Good. I'm just going to divide the coefficients. Now, the one difference here is, so I will say that, yeah, so you're going to divide your coefficients. Imagine, though, plugging negative infinity into kind of the top and the bottom here. So whatever that negative number is, however big it gets, in the bottom, you're going to square that first, right? Which is going to make this overall a positive number, which we need because we can't take the square root of a negative number, get a real number. So this is going to be positive. But when you're plugging in negative numbers to the top, what sign are you going to get always on the top? But you're going to get a negative. So this is going to be large negative divided by large positive, but they tend to keep pace with each other. So that's going to give you, instead of 1, it's going to give you -1. So the limit here is -1. But if these were positive, if this was limit as x approaches infinity, it would be positive or positive, so it'd be positive. So the interesting thing about this graph, so if you actually graph this out in a calculator, again, not a classical rational function, but the look of it would be similar to a rational function, but you would actually end up with basically 2 horizontal asymptotes. One horizontal asymptote at y equals -1, which the left end of the graph would obey, so at the left end it wouldn't cross it. And then one horizontal asymptote at y equals +1, which you would see on the right end of the graph. The right end of the graph wouldn't cross it. So this is kind of an interesting alteration of a classical rational function. Putting the square root down there, you essentially create sort of these 2 zones or, kind of 2 horizontal asymptotes instead of just 1. Good. But same pattern applies. So as long as you have a fraction, or you can think of your calculation as a fraction, the same pattern applies. Let's look at 23. Yeah, 23 is a good one to play with too. the limit as x approaches, I think, negative infinity. Yeah, -4 over 3 plus e -2x. And again, I want to bring this up because notice it's a fraction. So again, this is not a classical rational function, an alteration of it. But so this time our alteration is a little farther off because now we have an exponential function at the bottom. So now, unfortunately, we can't compare powers like we did with the last one. But what we can do is we can, again, going back to what we did in the first section, we can just basically calculate the limits as we go and then use how, again, these patterns about how we understand fractions work with calculations, with the calculation of fractions to kind of get our answer. So the limit as x approaches negative infinity for -4 is obviously going to be -4. So that stays, that stays. So the only thing that's really changing here is this e to the -2x. Now, if I do -2 times negative large number, what does this end up being? So it's going to be e to a large number. So basically what I'm saying is as x goes to negative infinity, this goes to infinity. And e to infinity, what's the limit for that? That's going to be infinity. So really this whole thing goes to infinity. So we're going to have -4 over 3 plus a large number. And so what is my overall limit going to be here? So -4 over 3 plus a large number. 3 plus a large number is going to be a large number. And -4 divided by a large number is 0. You're just going to keep getting larger and larger numbers in the bottom. That's going to go to 0. So again, this, maybe not the strict rule of this about powers, but the pattern of this, the bottom is progressively larger than the top. Limit goes to 0, always. So no matter what function they really put in this, so part of what I'm trying to show you then is, we start with your traditional rational functions, then we start deviating from that. But what I'm saying is no matter what function they put in there, you're still going to be able to use the general pattern to get your limits because it's a fraction. So that gets you any of these. So you can do limits as x approaches infinity or negative infinity for any function they put in there, as long as you just keep these patterns for horizontal asymptotes with rational functions in mind. So, actually, let's see. Yeah, honestly, I don't think we need any more. So that's it. That's limits at infinity. Like I said, it was going to be a very short. So you already knew it. You just got to take those ideas and use it. One, if they give you the rational function, you already know how to do that. It's like that's the classic. Then if it's non-classic, you still just take the same ideas and what you guys learned with limits, the first chapter. You're good. All right. That'll get you everything in 3, 6, and 4, 5. So I will see you guys. I'll come back. We'll do actually 5.6, which is what's called L'Hopital's rule. And you'll see that L'Hopital's rule we'll revisit one of the problems we have with limits and therefore finding derivatives from kind of chapter 2 and chapter 3. We already figured out a way to solve it. L'Hopital's rule gives us another way to solve it. And it involves derivatives. And sometimes also involves these limits at infinity. So it kind of naturally follows these two sections really well. But I'll see you guys back here for that section.